Oh, hey. Oh, I didn't see you standing there. Oh, but while you're there, let's go ahead and do some math. Let's talk about graphing a function rule. Okay, in order to do this, our main objective is to graph equations that represent functions. So we got all kinds of different functions. We got linear and nonlinear functions, and we're going to go ahead and graph them. And in these particular situations, I'm going to be giving you the equation so that you can indeed graph them. All right, so graphing a function rule. What is the graph of the function rule y equals negative 2x, negative 2 times x plus 1? All right, so what I'm going to do is I'm going to first build out my table to get the different values. So I'm going to try negative 1 for x. So I'm going to plug in negative 1, so it's negative 2 times. All right, where were we? I lost track of thought here. Somebody knocked on my door and delivered like 14,000 Super Balls. Okay, they really didn't, but they did stop by. Okay, where was I? I got a table. Oh yeah, okay. So I've got this equation, and I'm gonna make this graph of it, and I'm trying with x is 1. Okay, I'm gonna substitute it in. So negative 2 times negative 1 plus 1. Okay, negative 2 times 1 is negative 2. Okay, oh no, that's gonna be positive 2 because a negative times a negative is gonna be positive, so that's 2 plus 1, so this is gonna be 3. If I use 0, negative 2 times 0 plus 1 will be 1. If I do 1, negative 2 times 1 plus 1 is going to give me negative 1. And if I do 2, so negative 2 times 2 plus 1 is going to get me to negative 3. I'm just going to plot those, and that should be enough to get me going here. So negative 1, 3, it's right there. 0, 1, so right there. 1, negative 1 is right there. And 2, negative 3, 1, 2, 3 is right there. And I can get a line out of this right here. It's going to be my line. Oh, that looks fantastic. Oh, that looks so great. I should take a picture. Instead, I'll take a video. Hey, why don't you press pause and you try this one? X, 1 half x minus 1. Pick a t-chart here. Why don't you go ahead and just pick some values, negative 1, 0, 1, 2, 3. Half of some of these numbers won't be fun, so actually maybe not those ones. Maybe we go with like negative 2, 0, 2, 4, 6. Those will be nice to do like halves of. Press pause, try it out. All right, how'd your graph go? Just had to keep track of my negative, halvesing it, and then minusing 1, subtracting 1. And then when I plotted out, I was able to put my points down, get my line going, and I can see that this function is a nice linear line. All right, a couple things you want to keep an eye on. There's such thing as a continuous graph, which is what we're doing most of. It is a graph that is unbroken, continuous information. There's also a type of graph that maybe we don't see a whole lot. It's called a discrete graph. This is isolated points. So the information that is between them, they're not connected because the information is maybe not valid. And we're going to look at a couple of examples of that one. So this one, when you're plotting it, it's just points on a graph. Again, not connected. We can see the pattern though. I mean, we can see that it's moving down at a set pattern, but it is a discrete one. So identifying continuous or discrete graph, a local cheesemaker is making cheddar cheese to sell at a farmer's market. The amount of milk used to make the cheese and the price at which he sells the cheese are shown below here. Write a function for each situation and graph them. Is your graph continuous or is it discrete? So we're going to look at a couple of these. The weight W of cheese in ounces depends on the number of gallons of milk used. So the more milk we have, the more weight of cheese we have. So I just drew a line in the middle of nowhere. So if W equals 16M, we make a table of values because we get that up here. Okay, so our 16 is connected here. And here's our table of values. 16 times 1 is 16. 16 times 2 is 32. 16 times 3. Okay, so our unit rate is 16. If we graph the ordered pair and look and see what this looks like, we can see that it indeed is, everything is connected. This is a linear relationship and it is continuous. It is continuous, which makes me think that this next one might be not continuous or discrete. So let's look. The amount made from selling the cheese depends on the number of end wheels sold. So here is our information, considering that each wheel costs $9. So my amount is $9 per each one I buy. Make a table of values. So if I buy one, it's $9. If I buy two, it's 18 bucks. If I buy three, it's 27, and so forth. Here is what this looks like. The reason why it is indeed discrete is because we're not selling a half a wheel, which would be right here. Or you cannot buy 3/4 of a wheel. Or you cannot buy a wheel 0.2. And that's what that line would represent. We would draw a line if you could buy little portions of them or decimal amounts, but in this case, we cannot. So we pull those off, and we can only sell these whole wheels. Thus, our graph is indeed discrete. The function rules graphed in that last problem represent linear functions. Nice linear relationships that are happening. You can also graph nonlinear functions, okay? So these are not linear, not going to be that unbroken straight line. When a function rule does not represent a real situation, when a function rule does not represent a real world situation, graph it as a continuous function. Okay, so if you can't tell, like if it's not attached to a story, just go ahead and graph it as continuous. But if the story tells you that there's no information in between the dots, then you just place them as dots or points on the graph. So these two right here, we're going to go ahead and, at least this guy right here, there's no story behind it, so we know that it's going to be continuous. We're going to connect point dots and then connect those. So let's try this. Oh, look at that guy. That's absolute value. Those bars are telling me absolute value, and absolute value represents the distance from 0. So I'm going to put a couple points down. We're going to do -4, a -2, a 0, a 2, and a 4. I just picked those one because I'm kind of planning ahead, and I see that I have to subtract 4 from it. Kind of keeping it nice and clean. You could still do -2, -1, 0, 1, and 2. You can totally do those ones. But let me look. So to solve this one, it is the absolute value of -4 minus 4. Okay, the absolute value of a number is positive, so the absolute value of -4 is 4. Minus 4, this is going to be 0. The absolute value of -2 minus 4, so the absolute value of -2 is 2 minus 4, so I'm at -2. The absolute value of 0 is 0 minus 4, it's going to be -4. 2, so the absolute value of 2 is 2. Now notice I didn't say the opposite. I said the absolute value, which is always going to be the positive version of it. It's always the distance from 0, and 2 is 2 away from 0. So the absolute value of 2 is 2, minus 4 is -2. The absolute value of 4 is 4, minus 4 is 0. Okay, so this is an interesting one, and this is what actually absolute value graphs look like. So when you see that you're graphing an absolute value, this is what it's going to look like. So -4, I'm going to pause it and graph it. All right, so I plotted my points here, and you can see that when I do an absolute value, it actually ends up creating this V right here. It is continuous because I don't have a story attached to it, but it creates this really funky looking V, which is kind of cool. All right, now this guy here, a little bit different. We got a square happening here. So when I square something, I'm going to give some values here. So I'm going to go -2, -1, 0, 1, 2. I'm going to substitute those in. So it's going to be -2 squared plus 1. Now this guy right here, I'm squaring also the negative. So it's -2 times -2, which is going to be 4 plus 1. So I'm at 5. Let's look at this guy. So -1 squared plus 1, which is -1 times -1, because of the parentheses, is 1 plus 1 is going to put me at 2. 0 squared plus 1 puts me at 1. 1 squared plus 1 is going to be 2. 2 squared is 4 plus 1 is 5. I'm going to press pause and graph this because I want you to see it. All right, take a look at this graph. Plotted these guys out. It is not a V. This one's rounded. Actually, we have a name for that one. That's called a parabola. So when you have something being squared, this is the graph it looks like. It is still continuous, connecting all the dots because we don't know what story this goes with, but indeed is a parabola. All right, I want you to graph this one. Oh, look at this guy. This guy's got a cubey to it. Okay, so go ahead. Keep in mind you're cubing. So build out a chart, X and Y, and try some values. Go into the negatives too, because you kind of got to see what's going on. So go -2, -1, 0, 1, 2. And then when you're filling in your Y, remember that you're cubing the whole thing. So this guy right here is saying -2 times -2 times -2. And it's the parentheses that are making that happen. All right, pause it, give it a try. Whoa, holy bucket of lava. Take a look at this guy. So this is the graph of when you cube something. Look at that. It kind of curves a little bit, arcs a little bit. Woo! That is a crazy one. But that's what's happening in this relationship. It is continuous. It's not linear. It is a function. There is a relationship happening here between x and y, whatever the story is behind it. All right. This is it. You keep practicing it. You are going to get fantastic at it. I'm going to go eat a whole bowl of Jell-O with my nose.